All right. Welcome everyone to the TAP Colloquium. It's a great pleasure to introduce Zoltan Haiman, who was supposed to be coming here in person, and then we had to reschedule, and then he got bumped to Zoom. So I'm sorry that we don't get to interact with you, but hopefully we'll get you out here some point in the future. Zoltan has worked on a really wide variety of topics in theoretical astrophysics. A lot of them are focused on black holes of varying ages and masses, everything from quasars, supermassive black holes, gravitational wave mergers, interactions between the binary black holes and their disks, and a whole host of related phenomena, reionization. I could go on, but I'm going to instead let Zoltan tell you himself about the exciting work he's been doing. And I'll just remind everybody that we would like to keep this talk interactive. And so if you're interested in asking a question, you are welcome to either raise your hand, your Zoom hand, or put a note in the chat. And if all else fails, you know, unmute yourself and your video and go ahead and ask a question, because we'd like to you know, make this a real dialogue. All right, with that, I'll turn it over to you, Zoltan. Take it away.
Yeah, thanks a lot for the invitation and introduction. It's a pity I'm not in Tucson, but hopefully next time in person. So yeah, I wanted to tell you today about work we've been doing the last few years on supermassive, mostly, black hole binary mergers in the context of both gravitational waves and also in the context of electromagnetic observations. So this image is supposed to show you that black holes are quite lively when they're surrounded by some plasma compared to just being in vacuum. This work is actually collaboration with Andrew McFadden's group at NYU, and lots of students and postdocs have been involved who are listed here. So I have to start with two non-scientific slides, which I already gave away because of by accident in the last minute or two. But I recently read something interesting about the origin of the word black hole, and since this talk is a lot about black holes, I wanted to ask you, people feel free to shout or jump in and say who coined the word black hole. So yeah, that's the question. Do you know who coined the term black hole?
Yeah, of course, it was John Wheeler. You gave it away, but I already knew about that. Okay,
anybody else? Well, that's fine. So yeah, so most people know that John Wheeler, who was at Princeton, coined the term black hole. But the reason I brought this up is because I read his autobiography recently, which was actually written a while ago. But this is what he says, that in the fall of '67, he was invited to NASA's Goddard Institute at 2880 Broadway in New York City, which was a workshop on pulsars, which were just discovered, where he said we should consider the possibility that at the center of a pulsar is a gravitationally completely collapsed object. I remarked that one couldn't keep saying gravitationally completely collapsed object over and over. One needed a shorter phrase. How about black hole? Asked someone in the audience. I'd been searching for the right term for months, moving it over in bed, bathtub. Suddenly this name seemed exactly right. So I find this fascinating because it's an he gives the credit to an unknown person, and also he explains the term got him very excited. And the next pages of the biography, he says black body radiation was already in common use, so this term is really perfect. And the other reason I'm excited by this is that this is the view from my office here at Columbia. I think many of you have been here. This is the main campus. If you exit on the right here, you get to Broadway, and you can walk past this place, which is a place I walk past every day in my way to the office. So this is a 2880 Broadway, and this down here is a restaurant many people recognize from Seinfeld, the show. So there's lots of tourists usually taking pictures, but the room where the black hole term was coined by the anonymous person is up here. These windows belong to the Goddard Institute for Space Studies. So I was amused by that, and I wanted to share it with you. There's actually some more complicated follow-ups to this story, but I'll save that until somebody wants to know about it. Okay, so on to the substance of the talk. Actually, I had a plan to do 4 things. First, I wanted to do an introduction, why mergers of supermassive black holes in galactic nuclei are interesting, and why we think we should be interested in those. And the bulk of this talk will be theoretical and asking questions about what a pair of black holes would do if there was a gas cloud in the shape of a disk around it, both in terms of emission, electromagnetic emission, and the orbital evolution. And then there are lots of observational questions, which I hope to get to. Some of them, the obvious one is that these are massive black hole binaries, are targets for LISA in gravitational waves. But it would be nice to see them also in photons, and we can do a lot with those. And then we can ask, how do these binaries look like prior to entering the LISA band or in the LISA band itself? There's also some recent observations of candidates for binary black holes, which are not resolved, but seen in quasar surveys. And then I'm pretty sure I won't get to this, but I recently started also doing some work on, analogous work on stellar mass black hole binaries with gas disks, which are relevant for LIGO observations. So if I have time, I'll comment on those. So in terms of the first part of the talk, the motivation is actually quite straightforward, but I just want to go through it a little bit. So we know, of course, that most major galaxies have, at least in the nearby universe, have a massive black hole in their nuclei in the range 10 to the 6 to 10 to the 10 solar masses, correlating with the size of the host galaxy, roughly weighing 0.1% of the mass of the spheroid components of the host. So these galaxies, which carry black holes, we also know are built up in hierarchical structure formation models due to a sequence of mergers. Typical galaxy experiences several major mergers in a Hubble time. And we know that, of course, from theory, from modeling the buildup of dark matter halos and galaxies, but also observationally, we've counted number of merging pairs of galaxies on the sky. So these are pretty secure observational results over the last 2-3 decades. We also know, third point, is that most galaxies have some gas in them. So because of this correlation that we've established, we know that sort of low mass half of this range of supermassive black holes, they reside in gas-rich disk galaxies. So up to a few tens of millions of solar masses in the black hole mass. Now above that, the most massive supermassive black holes, approaching 10 to the 8 or 9 solar masses, they tend to live in massive elliptical galaxies, which are often caricatured as dry ellipticals. But in fact, even ellipticals have gas in them, in the nucleus, and which can often be as much as 0.1% of the stellar mass. So enough in principle to dynamically affect black hole binaries with the comparable mass. And then the fourth and last bullet is, we know quite well for many decades of theoretical work and hydro simulations that when two galaxies collide, then the massive black holes would be brought into the new bulge, sort of kiloparsec size, by dynamical friction on stars and the dark matter, and end up in the new nucleus. We also know that gas that's originally in the individual galaxies is torqued by the merger, and we understand the reasons for that is the misaligned bars which form between the gaseous and the dissipationless components of the galaxies. So this gas flows, its angular momentum is removed, flows to the nucleus. It cools rapidly, the cooling time is short, and forms a disk in general. So bottom line, we expect it's a common outcome that of galaxy mergers, that there's a pair of massive black holes with a circumbinary gas disk. Now, have we observed these? The answer is not quite. There are a few examples of pairs of active black holes in galactic nuclei, the poster child of which is this X-ray image of a galaxy called NGC 6240. And it has two nuclei, both of which are active. So it's effectively like two quasars. The projected separation is a kiloparsec. There are a few dozen other such resolved dual or binary quasars with separations of few or tens of kiloparsecs. There's, if you ask what is the record holder in terms of the most compact binary we've seen, it's a radio galaxy seen by VLBA interferometric observations, where the projected, and again, both components are active and the separation is 7.3 parsec. So just in terms of what separation is small versus large, it's good to compare this to this sphere of influence. So if you take the scaling relations I mentioned between black hole mass and host galaxy, sigma here is the velocity dispersion of the host in units of 200 kilometers per second. This is the black hole mass in 10 to the 8 solar masses. And the sphere of influence of a black hole, if you place such a black hole in this host galaxy, is about 10 parsec. So the answer is that we haven't quite seen a genuinely bound, gravitationally bound binary, except for perhaps this most compact one case of the radio galaxy, which is more compact enough that its orbit is dominated by its own gravity rather than stars or gas in the galaxy.
Quick question: what fraction of things that have been observed at sufficient resolution that you would be able to identify these with something like VLBA?
So I think of order 10 galaxies, we would resolve the sphere of influence directly.
Okay.
On kinematics. I mean, there's about 100 galaxies where there's, as you know, local galaxies where black hole masses are measured. So even if you don't technically resolve sphere of influence, if you resolve 2 or 3 times that, you can still fit a kinematic profile and find the black hole mass. So maybe a few dozen. So yeah. Now the question is, if you have so we don't commonly see smaller separation binaries, but they might be there, of course. They must have shrunk, they could have shrunk to smaller separations, which we don't resolve. And the question is, what then happens? Do these black holes produce mergers, or do they stall? And this is often called the final parsec problem. And we know that one number is secure here, which is if you had no gas or stars around, then we know that binaries would still merge. They would emit gravitational waves and call eventually in spiral and merge. So here the interesting number is how far, how big a separation should these binaries have such that they merge in 10 billion years. So for the low mass end, 10 to the 6 solar masses, this is a milliparsec. For the very highest mass black holes, 10 to the 10 solar mass, if they're separated by 1 parsec, they merge in 10 gigayears. But the answer is basically that there is an unknown bottleneck here, because we need to get to these small separations, which are quite a bit smaller than what we've resolved in observations, in order to guarantee the merger. So that's what stimulated a lot of questions about this so-called final parsec problem. In the presence of stars or gas, it's possible to extract energy, the binary's orbital energy and angular momentum, and shrink to these smaller separations. So I will talk about this in my talk, how that works with the gas. Just want to say a couple more things. So first of all, one reason to work on this is that gravitational waves are targeting supermassive black holes. So this is a spectrum of gravitational waves. You've seen many examples of this. This is the LIGO band, where it detects stellar mass black holes of order 10 to 100 solar masses when they merge. This is the future space interferometer LISA, which would be sensitive to 10 to the 4 to 10 to the 7 solar mass binaries to very high redshifts. And then pulsar timing arrays are in the lowest frequencies, nanohertz regime, where they probe the very massive end of this mass function. And the reason I decided many years ago to focus on massive black holes is because, as I just explained, at least the conventional wisdom is that these mergers do take place in gas environments with gas around the black holes, whereas the standard thinking for stellar mass black holes is that they take place essentially in vacuum. There's not much gas around stellar mass binary, but I put question marks here because none of these are rigorously proven or guaranteed. But in any case, most of the talk I want to focus on these massive black holes. This is my last motivational slide, but I do think it's important to emphasize why you should be interested in gravitational wave sources, which are also seen in electromagnetic radiation. So nowadays, this is called multi-messenger astronomy. But essentially, the point is that if you detect both gravitational waves and photons from the same binary or same population of binaries, you can do a lot more science than with either of these alone. So roughly speaking, in two kinds of things. One is for astronomy and astrophysics. The extra science you could do are the following. So you would, for the first time, you could study accretion physics in a regime where you know the black hole masses and parameters, spin and mass and orbital parameters. And you could study the light curve and the spectrum as a function of these, which is unprecedented. There's a second kind of thing which can help with accretion physics, which is the gravitational waves themselves might be distorted by the presence of gas. I hope to get to that in my talk. And that tells you about the gas environment of the sources detected by LISA. We can also learn about the long-standing issue of galaxy and quasar coevolution. We know galaxies and quasars, the population evolves similarly, they rise and fall together. So if you knew if you had the detection of the black hole in electromagnetic radiation and could identify the host galaxy, you would know which galaxies carry what mass black hole mergers, and you could have severe constraints on this coevolution. We could also study the assembly of the first massive black holes via how they assemble via mergers and accretion. Mergers would be coming from gravitational waves, and their growth due to accretion would come from electromagnetic observations. Another interesting question, intermediate mass black holes, do they actually exist, and in what environments do they form? Again, you have to detect them and trace them in the host galaxy, not just gravitational waves. And in the stellar mass case also, there's lots of discussion now about how you form the stellar mass black hole binaries that LIGO detected, and seeing photons from any of those would be a great new constraint. And then fundamental physics and cosmology, there's also things you can do. I think most prominently, I think I won't explain this because now I think everybody knows by now that you can draw a Hubble diagram from a binary black hole if you have the gravitational wave detection and gives you the distance, and you have an electromagnetic detection which gives you the redshift. Then you can study distance to redshift relation, which is especially interesting given the current Hubble tension, where it's apparently the case that very low redshift expansion rate and Hubble parameter doesn't match the one measured by the CMB. So from supernovae, it doesn't match the Hubble constant measured at high redshift from supernovae. So it would be nice to know, have a single Hubble diagram covering a very large redshift range, straddling these two, and maybe will help solve this puzzle. And I think maybe even more exciting is that if you have these Hubble diagrams from the standard sirens, you can compare them to the Hubble diagrams from supernovae, and one is based on gravitons, distances from gravitons, the other is based on distances from photons. So if we have gravitational theories which differ from general relativity on cosmological scales, these two might disagree. Likewise, photons and gravitons might travel at different speeds, which could be discovered in these multi-messenger observations and give you constraints on various theories, including massive graviton or extra dimension and such. And if this speed difference is found to depend on frequency, we can particularly explicitly check Lorentz violating theories. All this requires detection of gravitational wave source with photons as well. And of course, last technical motivation is if you have a marginal detection with LIGO or LISA, and you see an EM counterpart that could solidify this detection. Okay, so that was all the motivation. So let me now get to the bulk of the talk, which is what happens to a black hole binary surrounded by a gas disk. So the approach here that we followed in the last 10 years or so is actually quite simple. We know how, roughly at least, how quasars operate. There's a single black hole here. There's a smooth and steady gravitationally stable accretion disk, geometrically thin. And then there's an outer region, which is gravitationally unstable and providing the fuel that settles into this disk, where the Tumbre parameter falls below 1. So in this talk, I'm just going to focus on this inner region, which is a subparsec region. So I'm just assuming, completely evading the question of how the binary maneuvered through this gravitationally unstable part of the disk. So let's just do a very simple problem, which is, suppose we have this simple near Keplerian disk with 2 point masses instead of 1 point mass. This is a very simple setup. It's almost like a textbook problem, but the things that I can answer or show you with this very simple setup is answer questions about electromagnetic signatures. So we want to know very basic questions. Does the gas actually end up being captured by individual black holes and get close to them so that within 10 Schwarzschild radius, let's say, so that the objects can be bright even at the merger? This is very important for observability. So how do these black holes accrete? What is their luminosity, spectral shape variability? Second important question you can address this is orbital evolution. So the gas disk around the black holes will torque, can extract energy and angular momentum from the binary. So the question is, does this help or hinder the merger? And if it helps, can you actually merge or get to these small separations for gravitational waves to finish the job within a Hubble time? It also affects observability, because if gas disks make binaries spiraling very rapidly, that means we expect fewer such objects on the sky at any given moment. If the in-spiral takes longer, we expect more such objects. So if you want to predict populations on the sky for observers, you need to know the details of this orbital decay speed. Third question I mentioned earlier is, can we actually see your electromagnetic emission even at the moment of the merger, when the black holes are very close and kind of ran away in a very rapid gravitational wave in spiral? And can the waveforms at that moment, the gravitational wave emission, be modified by the gas? So I'm going to skip. Well, there is a cartoon picture of this setup, which is there's an accretion disk, there's 2 point masses, and we know that there are no stable orbits for particles to coherently orbit this binary within this region, which is about twice the binary separation. So there has been a naive cartoon picture for a while, which was like this, that the black hole binary ejects gas fluid elements which try to enter this cavity. And so in contrast, what we've done here is numerical simulations, which are essentially the simplest possible things you can do to investigate this system of binary black hole plus disk. So they were done, most of the things that I'm talking about today, with the code Disco, although a couple of results are from a newer code, Mara. Disco was written by Paul Duffel, and Mara was written by Jonathan Drake. They're moving mesh grid hydro codes. So we just do pure fluid dynamics. We solve Navier-Stokes equations essentially in 2 dimensions. We can put pseudo-Newtonian hydrodynamics using Vita-Paczynski potentials rather than Newtonian potentials. The viscosity in these disks is alpha viscosity. the thermodynamics is either just simply assume the disk is isothermal, or we assume the disk cools due to black body radiation on the surface. So it's assumed to be optically thick, which is generally an excellent assumption. And it's heated by viscous dissipation and by shocks. The black holes are on the grid. So we follow the gas approaching the individual black holes, and they accrete via a sync prescription, which we have to implement. And we set up initially steady single black hole disks in near Keplerian motion. And we can set up this disk to be very, very large, extending out to 100 times the binary separation, just to make sure that the disk is not affected by boundary conditions. And we can run this for thousands or even 10,000 orbits of the binary, so that we reach a steady state behavior. So we can run this for a viscous time, meaning there's a viscous time here at the 2-3 times the binary separation. And we can run the simulation long enough to exceed that viscous time. And then in this kind of simulation, they're so simple. There's basically 3 interesting parameters. The ratio of the 2 black holes' masses, Q, the eccentricity of the orbit of the binary E, and then the disk temperature, or equivalently, its Mach number or aspect ratio, H/R. And I think, so I'm gonna mostly focus on Q. I think I briefly mentioned these last 2. And so I'm gonna just show you to get to the bottom line, just one movie, which I think illustrates essentially all the main results that can be extracted from these kind of simulations. So this here is a binary black hole. This is the 2-dimensional disk around it. This is the surface density. So yellow is high, black is low surface density. And this is a movie in the co-rotating frame. So the black holes appear stationary because the frame is rotating with the black holes. And what you see here is the behavior of the gas, which, I mean, the most conspicuous feature here is you do clear out this cavity. That confirms the cartoon picture that you cannot have gas stably accreting in this cavity. But you see many other very obvious features. So first of all, you see the gas does get to the black holes through the streams which come into the cavity. And you see that this cavity is quite distorted with these hotspots, dense spots along the rim of the cavity which revolve around. So all of these are actually quite interesting and important for observations. So here are the summary. So there is.
Before you move on, there's a question from Roger Thompson.
Yeah.
Oh,
Roger. Hi.
Just to make sure that I understand the setup, I assume that the binary black holes have the same plane as the disk, and are they rotating in the same direction, or can they be rotating opposite?
Yes. So it's 2D simulation. It's all coplanar and all prograde.
Okay. Thank you.
Yeah. So there is the most conspicuous feature is this cavity. There is the wall of this cavity has this lump, which we actually understood is a genuine instability. So the streams which are flung around by the black holes. So some of the gas that enters this cavity is captured by the black holes, but a large fraction, let's say half or actually more, is flung back outward and hits the cavity wall and causes these shocks. And this process runs away in an asymmetric fashion. So if there's a little asymmetry, it tends to be enhanced by this slingshot mechanism, pulling gas in and slinging it back out. The streams become lopsided. One stream is stronger than the other and causes concentrations and lumps of mass at the cavity wall, which then make the streams even more asymmetric, which makes the cavity wall even more lopsided and the lump even stronger. So this is a runaway instability. which is quite robust. Actually, several other groups have done simulations and found similar behavior. The other important point to see very clearly in this picture is that some gas does get to the black holes. They form these mini disks, and the mini disks are, actually you could see in the movie, they're strongly fluctuating in this movie. So maybe the most, well, there's some couple of important basic questions which I think is worth dwelling some more about. So the first question is, why does this binary accrete at all? I mean, normal accretion disk with one black hole, we know what happens. There's a standard paradigm where you have an accretion disk which has some viscosity. The viscosity is due to the MRI, or perhaps some other global magnetic phenomenon. But the point is that the angular momentum is transferred out by viscosity, and that allows mass to continuously flow inward. So here, I believe there's a completely different reason. There's accretion, which has to do with shocks. So this picture here is a snapshot from the simulation, shows again the density, but also shows the velocity field, and shows that, for example, when I'm pointing here, this material is actually moving away, outward. This circulating gas is nearly Keplerian, but then it collides with the outgoing stuff. So that changes the angular momentum. And essentially, the shocks which change the angular momentum is what causes the accretion. So I think this is really nice to illustrate with an even simpler setup. So this picture here shows an experiment you can do at home yourself. So this black annulus here is just a bunch of massless test particles. So no hydro simulation. These red dots are two black holes. And here I just solved the orbits of a large number of massless non-interacting test particles. And again, in the correlating frame, they're initially located in a circular orbit. After a quarter of an orbit of the binary, you see that this quadrant is pushed away and this quadrant is pulled in. And that gets enhanced after half an orbit and 3/4 of an orbit of a binary. You tend to produce trajectories of these test particles, which basically lose angular momentum, although angular momentum is a fuzzy concept here in the three-body case, but essentially you're pulling in particles in two quadrants and you're pushing out particles in two other quadrants. And now this is a non-interacting test particle. So you have to throw away this kind of simulation of orbits because the orbits cross. So over here in this finger, the orbits start crossing each other, and so you can't trust this simple exercise.
And
but you see what happens.
A quick question as well. Go ahead, Vasilis.
Yeah.
So Zoltan, if the tidal torques are essentially, because in the case where you have the massless non-interacting, it's the tidal torques that essentially are stripping the particles toward the vicinity of the binary. So what is it that makes you say that it's the shocks that are induced in the hydrodynamic case that are leading to the accretion, given that even in the purely non-interacting case, you still have particles moving toward the binary? I assume that if you were to evolve the picture in the non-interacting case further, we would actually see maybe some accretion there too?
So no, because yeah, very good question. So I cannot show this. If I try to show this a little later, it will be completely incomprehensible, because what you would see is a huge mess. These particles which are pulled in, then they start to go on very strange chaotic orbits, and it would just be all a mess. But none of them would actually really come within, near the black hole.
Yeah, if you look at the sort of the zero velocity curves for any test particle that starts out well outside the binary orbit, you'd find that basically the entire black hole is encompassed by a zero velocity curve, so things can't penetrate; they just get ejected.
Yeah. But I'm just showing this simple exercise because, and also these orbits cross, so there's no real point of following these orbits afterwards. So we know there are shocks. because when two orbits cross in this non-interacting particle case, in the hydro case, there is a shock there.
Yeah. So, but I was going to say another thing. But in the case of a black hole, you're also going to have an innermost stable orbit. So, so I'm just curious if particles that do approach the innermost stable orbit do get accreted, even in the case where you have the non-interacting particles, because of general relativistic effects. Essentially, that's what I'm asking.
Yeah, I think that's correct. What you just said, they can be accreted.
Probably wouldn't be enough to explain the total accretion rate that you see in the hydrodynamics.
So then I found, yeah.
I'd have to check. I actually think that maybe I think that may not be true if you do not have any extra mass to exchange momentum with. I think you might actually be totally forbidden from accreting formally in the restricted three-body problem if you start with things entirely outside of the binary orbit because of the conservation of the Jacobi constant.
Yeah. I think, yeah, maybe once you're inside the ISCO, I think you can actually end up being accreted.
Yeah, I would think so, yeah.
But
I'm not sure you can get there is the question.
Yeah, but I think, so yeah, now there's no scale in these simulations. So I'm actually thinking here outside, well outside ISCO. So 100 Schwarzschild radius. I'll come back to that. I actually will come back to this in a, so maybe we can hold off. I think the main point here, which I think is very robust, is that there are shocks. They occur exactly where you expect based on these toy models. You see them in the simulations. There are shocks, and they remove angular momentum from the gas at a rate that allows them to move inward. And so this we have further diagnosed with, you know, if you look at angular momentum flux, you can actually see a steady state where these shocks are important. But
Roger, do you still have a question, or is your?
Yeah, I do. Can you really, in a two-dimensional simulation, understand what's happening? Because we know in the real objects, there's these jets that are going perpendicular to the plane, and they have to be doing something to the mass distribution.
yeah, so that's a very good question. I think, yeah, that's a major caveat, and there are many more actually. So this is a very simple setup. I think jets are very likely, in fact, because I think it's very likely that at least one of these black holes will be either sub-Eddington or super-Eddington and drive a jet. Maybe if the jet is pointing perpendicular, then maybe on these smaller scales, it won't have a major impact. But we just don't have it in these simulations. These are just 2D. Now, it is justified, at least in the sense that these are thin disks. We can verify that they remain thin in the simulation, even when the shock heating and the viscous heating causes the gas temperature to rise. So H over R becomes larger. But generally, we have verified that it remains 0.2 or less. So at least geometrical thinness is justified in principle, unless you have super Eddington accretion rate. Okay, so let me get to a couple of points in addition to this. So the other question you should ask is, what is the accretion rate? That's obviously important. And so here I'm actually showing two other simulations which are unequal masses. So the general, well, so the right shows a simulation where the mass ratio is 0.7. The left shows a simulation where the mass ratio is 1 to 9. And this plot shows m dot in units of m dot 0. And m dot 0 is a reference simulation we run with exactly the same initial setup, except for having only one black hole instead of two black holes. So 1 here means what we would get for a single black hole. Green is the accretion rate on the secondary, the lower mass black hole, and blue is the accretion on the primary, the higher mass black hole. And you see something very obvious and clear here, which is that well, first, I think most importantly, the accretion rate is not much less than 1. So So this number is actually, if anything, the time averaged is even a little larger than 1. So in fact, despite this large cavity and feeble-looking streams, the rate at which the secondary black hole is eating the fuel is actually not at all diminished compared to a single black hole. Second obvious point is that the secondary is way out accreting the primary, and that's for a simple reason, and that the secondary has an excursion from the center of mass, which is larger by a factor of 1/q than the primary. So it gets first pass at the stream spilled off the wall of the cavity. So it's accreting much more rapidly. That tends to drive the black hole towards equal mass. And then the third obvious feature is that it's very periodic, very clearly following the orbital period. This plot is actually over 25 binary orbits, and you see 25 cycles of accretion with quite large amplitude variability. This is just a periodogram. And this is actually strikingly different for a more equal mass black hole, where it's more towards unity. And in fact, there is a transition at about 0.3, where this behavior changes from the left to the one on the right. The one on the right, again, the sum of the m.1 and m.2 is the sum of green and blue, is again not diminished compared to 1. So it's still, the binary is still accreting the same as a single black hole. And it's still periodic. You can see by eye, however, that the strongest period, for example, in the green curve, which is the lower mass of these two almost equal mass black holes, is actually more like 6 orbital periods of the binary. And this is the periodogram in the bottom, and it does have a peak at much lower frequency. It also has the peak at the binary orbital frequency. But this modulation on the lower frequency is basically coming from this lump. So that's why I took time to explain the fact that the rim of this cavity is not axisymmetric. And this non-axisymmetry, it modulates the accretion rate at a low frequency, roughly corresponding to the orbital frequency at the wall of this cavity. So these are obviously very basic things that you could look for in observations. This kind of structure where you have two prominent periods separated by a factor of a few. Second important point I wanted to make in terms of observations is the spectrum. So again, these are toy simulations. We can measure the spectrum by assuming that each patch of this disturbed gas disk emits blackbody radiation. And again, that's justified in the sense that we can go back to the simulation when you scale it to some external m dot and calculate the optical depth and the geometrical thickness based on the temperature. And these are still optically very thick, geometrically thin disks. And so the spectrum of such a disk, the outer region shown in red, this is a spectrum where it's basically a composite spectrum over the entire disk, blackbody radiation summed over the entire disk. The red is the outer disk, so outside the cavity. And it basically behaves like a normal Shakura-Sanyaev thermally emitting Shakura-Sanyaev disk, except the inner rim of the disk is hotter, so it's extending to higher frequencies. Then the mini disks are in orange. They're much hotter, and they're contributing almost the same amount of energy emission as this circumbinary disk. So the circumprimary and circumsecondary disks in total are a factor of, here you can see more than 10 times hotter. And because of this cavity, if there was nothing else except for two circular mini disks and a circular circumbinary disk, you would have a very characteristic dip in the spectrum, which is analogous to protostellar binaries with cavities, which have been, which is a standard technique actually in stellar binaries, or to look for companions or even planets, which create regions with gaps in the disks where there's no emission. This is a little less clear here because we found the streams in the cavity are also hot and they're shock heated, and they contribute less emission, but they do fill in this notch to some degree. So that, so again, I think the robust part of the spectral prediction is that the binary can be brighter than a single black hole because the gas is hotter because it's heated in addition to viscosity. It's heated by shocks. And ultimately, it's using the energy, binding energy of the binary. So you have not just viscous dissipation, here you have another energy source, which is the binding energy of the binary, which is sloshing gas around, causing shocks and heating it. So this is brighter than a single black hole case. And because the material is got these hot components, it also has a different spectral shape extending to harder thermal emission than single black holes. So that's, yeah. Was there
this? Since it's not viscous, the shocks that are doing the heating, do the outer portions of these disks have a different spectrum than the classical due to the 1/3 that a viscous disk has?
So the outer regions are unmodified. So this red curve here, the lower frequencies are the same as a normal Shakur-Sev. No difference. Only the hotter inner regions modify their shape.
Okay, thank you.
So the third thing I wanted to mention, because we're on the topic of electromagnetic telltale signatures of binaries, is something that happens after the merger. So this is, so you can forget the simulations I just described for now. There's another effect that happens after the merger takes place. This is actually, this topic was fashionable 10 years ago. And I suppose now it's a little less of a hot topic, but nevertheless, it's an important point, which is if you have a disk circling around the binary. So in this top panel, I'm again doing my toy calculation of massless test particles, which were placed around the binary, but I zoomed out a lot. So this cavity here, if you want to think of it this way, is let's say 100 Schwarzschild radius, the size of this cavity. There was a binary in the center which merged, and then after the merger, the gravitational wave burst, carried off a few percent of its black hole mass, and also caused the recoil of the remnant black hole at a few hundred kilometers per second. So the orbital speeds here would be about, at 100 Schwarzschild radius would be 2,000 kilometers per second. Out here might be, sorry, 20,000 kilometers per second, and out here might be 2,000 kilometers per second. This kick is a relatively small perturbation of the orbital speed, but you can see that these particles start to go on ellipses and make these concentric rings where they cross each other's orbits and accumulate. So this is a very interesting behavior, and same kind of thing I mentioned during the accretion. You essentially have every circular orbit becomes distorted and becomes an ellipse. So you have epicyclic oscillations at each radius, and they always oscillate at the local epicyclic frequency, which is just the Keplerian orbital frequency. So the oscillations are much slower out here and much faster here, and there are certain radii at certain times where there's collisions between nearby oscillating shells. And this the bottom is just a hydro simulation of the same setup, where you see concentric shocks moving outward. The speed actually at which this pattern moves outward is just the kick velocity, the recoil of the black hole remnant. And this is a chance of a afterglow. So I won't go into details here, but this afterglow is kind of unusual in the sense that it brightens over time and also hardens over time because the perturbations to the orbits out here due to the recoil are a larger fraction of the orbital speed. So the amplitude of the epicyclic oscillation is larger, and the collisions happen at higher speeds than here where the orbits are very tight and remain nearly circular. So the shocks are stronger out here than in here. So you get a brightening and hardening afterglow, which hopefully can be distinguished from other kinds of transients on the sky. Okay, so that was my topic on electromagnetic emission. So the second issue to address, which is very basic, is the orbital evolution of the binary. So this is now a very interesting topic. In the last couple of years, there have been 3 groups actually, which worked on this. So let me spend the next 3 minutes on this. So this is actually from our paper from 3 years ago by Tang. What I show here is the same kind of binary simulation I started with, except the only difference is this is an orbit averaged surface density distribution. So it looks much more coherent than the movie that I showed, because it's been time averaged over 100 orbits. But you can very clearly see the same features. There's a mini disk, which when you time average it, actually has a very distinct path shape, and you can see these wakes and the very characteristic shape of the cavity on this yin-yang shape. Now, the important thing you can ask is, how does the orbit of the binary get affected? And it can be affected by 2 things. One is the mass that's around it over here in this box is just exerting gravitational force on the black hole. So it's a direct gravitational torque. The binary is also accreting mass, and it's also accreting momentum, which changes its orbit. So basically, I'm going to ignore the second, because the second kind of effect, because we and others have found that by far the dominant effect is the direct gravitational torque. So the right panel here shows the surface density distribution of the torque. Red means positive, blue means negative. Therefore, obviously, you see the pattern is that there's a black hole here, there's the same black hole, same mass black hole on the other side. All the stuff in front of the black hole is red. It's pulling the black hole forward. So it's giving angular momentum to this black hole. All the stuff behind it is blue. It's pulling the black hole backward and removing its angular momentum. And what you see here is it's almost symmetric. You can see the shape of the mini disk on the left, that it's almost, but it's not exactly symmetric in terms of back and front. So the stuff ahead here and behind the black hole definitely have different. There's a sense of direction of motion, and there's a slightly different shape of the mini disk and surrounding material. In particular, there's this little arclet sticking out. And the net torque on this binary is the difference between the red and the blue. And the exciting conclusion that was found by us and also a group in Princeton by Jim Stone and collaborators, and also by a group at Cornell by Dong Lai and collaborators. So these are the 2 other papers, which showed that you can actually kind of see by eye, but it's very hard to do a subtraction multiplied by 1/r² by eye. But you can kind of see there's a little more red close to the point here than blue. And the net effect is that the binary is actually gaining angular momentum, and is, instead of shrinking its orbit, it's actually out-spiraling as a result of the gas disk. And if you scale this to some physical numbers, you can assume that the accretion, everything here scales with the surface density of the disk, because this is just gravitational torques. If you scale the disk density to 0.3 times the Eddington value, you roughly find that it takes few million years, very roughly the viscous time basically, to move these black holes farther apart by a factor of 2. Now this conclusion caused a lot of consternation, because that's very bad. At least if your goal is to use the gas disk to make black holes merge, this is actually the opposite. And luckily, I'm gonna dispel the panic because we did 3 different follow-up investigations to this conclusion. So this conclusion that I just stated was for assume 3 things. The binary is on a circular orbit. The disk has a fixed temperature, which is such that h/r is 0.1, so Mach number is 10. And the third is that it's an equal mass binary. So we started one by one relaxing these assumptions. So the first one, which I think is probably the most interesting, is the Mach number. So here's a picture from recent paper by Chris Stede, who's a student. And the disk torques and the orbital evolution basically changed dramatically. So the top panel is the same that I showed before. Surface density is actually even a more high resolution simulation. H over R is 0.1, 2 black holes. You can see, sorry, the scheme of color is different in this paper, but again, the green is in front, the purple is behind, and the net effect is positive torque and out spiral. The bottom shows the same simulation, but with a 3 times colder disk. Now remember that for AGN disks, generally they're quite thin. So this number in a realistic AGN disk is 10⁻² or 10⁻³. And it's for numerical reasons that every group tends to pick this fiducial value of 0.1. So these disks are effectively 10 to 100 times hotter than they should be for numerical reasons. So if you try to fix that and make it 3 times colder, so H over R now is 0.03, you can see by eye that if you look at the surface density distribution, there's higher density. The density scale is on the right here. Yellow is high density, black is low density. So you can see the overall gas buildup is higher in the bottom panel than the top. And if you look at the torque distribution, you can see that this quadrant and this quadrant both got strongly enhanced. So it's, I forgot to emphasize that, but I kind of made it clear that in the previous case here, all the torques is just coming from the gas very close to the black holes. And what we find here is that that changes. When you make the gas thinner, the disk thinner, there's a larger pileup that occurs here. And the purple, you can see by eye, wake is now very strong and is closer to the black hole, and it wins over the previous torque. So now the torque is actually dominated by the material that's farther from the black hole, and the net balance, the sign switches. This gas behind exerts stronger torque than this gas in the front. So the net effect is roughly same order of magnitude torque, but the sign is changed from plus to minus. So we can relax and say that this disk is actually causing an in-spiral on potentially timescales of tens of millions of years. I'm going to skip this. So of course, I'm running out of time. So I'm just going to have to say in words. So ignore the plot here on the left. It just shows as a function of Mach number, the torques become more and more negative. But the bottom line conclusion is that if the Mach number is basically 0.025 or basically the Mach number is 25 or higher, the disk causes in spiral rather than out spiral. We also found if you have an eccentric binary, even just a little eccentric, 0.1 or higher, once again, the in spiral occurs, so no more out spiral. And we also found that for unequal mass binaries, although here you have to make it quite a bit unequal, so 0.05 or less, then again, the sign of the torque changes. So these are good news. And the third topic, which I was going to say, had to do with a
quick question before you move on, and then also just to note we are at 11.
Yeah.
Go ahead, Vasilis.
Yeah, so one of the things that happen when you have these shocks actually taking place and the binary also launches these spiral waves in the disk that also heat the disk, right? And because they steepen and they create shocks within the disk further out. And so I'm just curious if the fact that you're finding that for a H over R less than, let's say, 0.03 or so, you get an in spiral, if you let that evolve for a longer time, could it be that you can heat up the disk because of the binary heating it up, that you go up the H over R, the limit, and then you actually turn back into the torque being positive instead of negative?
No, that's an excellent question, and we have to do this self-consistently. So I don't know the answer to that question. It's a very, very good question.
Okay.
These simulations, just for simplicity, were isothermal. We have done also simulations with non-isothermal, but we haven't done these two together. And you're quite right. You have to check that the heating of the disk doesn't reverse this conclusion. I don't really have time actually to say much more. I was gonna, maybe I just end with one more point, which would be the third. So if I go back to my, I'm just gonna go back to this. So the main conclusion I drew here is that the disks are bright, the binary is a very efficient propeller, it makes a big cavity, but doesn't suppress the accretion at all, and makes a very characteristic variable electromagnetic light curve with an unusual spectrum. I also, for orbital decay, I just said, I'm reiterating that I think we can actually have quite rapid in spiral. The third thing, which I'm just gonna say in words and not show any results, but there's the question of, can we see concurrent electromagnetic emission? And the answer to that is again, yes. And that was actually an interesting thing which I could have gone into, but I don't have time. But the punchline is that there was a fear or conventional wisdom that once the gravitational waves become very rapid, much more rapid than the viscous time in the nearby disk, then this poor LISA binary will run away so quickly that it completely leaves behind all this gas that I just discussed. And when the LISA merger happens, the gas is very far away. You know, it's left at whatever, 50 or 100 Schwarzschild radii away. But we've done a simulation where we did include the gravitational wave in spiral, so very similar to the ones I showed. And the upshot is that the gas is actually able to follow the black holes all the way to the merger. There's almost very little suppression on the accretion, even at the moment of the merger. And the physical explanation for this is what I went through in detail, is that the angular momentum transfer of the gas is not due to viscosity. So the viscous time is long compared to gravitational wave in spiral time, but the shocks occur on the orbital time. So you can keep pulling off these streams from the cavity wall, and they shock per orbit, and they can follow the inspiraling binary. We also found that there's enough gas nearby that can actually distort extremely small distortions in the LISA waveforms, but could be detectable in principle. Sort of 10⁻⁴ or 5 effect on the LISA waveform due to the gas disk, but it could be detectable by LISA. I think I'm gonna just stop here. Sorry to have run out a bit of time, but so I'm not gonna show my concluding slide because I just summarized my main conclusions here. And I guess I can take 1 or 2 questions, then I have to go and teach my class.
All right, thank you. If you have a question, why don't you just to expedite things, just go ahead and chime in real quick. And I'll just note that if you want, Zoltan has made himself available to meet, and I'm posting a link to a schedule in the chat.
Yeah, I'm happy to follow up by email if people have questions.
I guess I have to ask this. There's an immense amount of energy being emitted by the jets, and that has to come from somewhere, which I assume comes from the energy of the spiraling black holes. So if you don't take that into account, can any of this be really considered the final word?
Well, yeah, again, so the answer is no, this is absolutely not the final word. I think jets can be, yes, can tap a lot of energy, either the binaries orbital energy or spins of individual black holes can be converted to jets, and also radiation. I'm even more worried about radiation because it's more isotropic. So jets, I think, could in principle be very collimated and not do much to the nearby gas. This general disk morphology might be a little more immune to jets, but less immune to radiation. And you know, there are many things to do after this. So we clearly eventually have to put in magnetic fields, do 3 dimensions. And Vasilios is actually doing a lot of this. Of course, then you can't do thousands of orbits, is the trade-off. Yeah.
All right, well, if there are no more questions, I'll just again note that there's a little bit of time left on Zoltan's schedule for tomorrow. I've also put in a shameless plug for the KATP workshop on this topic, if anyone is interested in learning more about circumbinary disks. And let's clap either virtually or in reality with an unmute. Thanks very much.
Thanks,
yeah. Thanks a lot.
Caitlin,
Thank
what's
you, Zoltan.
you referred?
Sorry, what did you ask, Silas?
This workshop you referred to?
There is a link in the chat now. It is a KITV workshop scheduled for spring of 2022 with the idea that maybe in principle by spring of 2022 it could happen on circumbinary disks in general. The application deadline is February 2021. And we are maybe somewhat behind on sending out our notifications about this, but we will try to do so soon.
No, thanks for remembering the plug. That's actually going to be a very nice workshop. I'm pretty optimistic we'll be there in person. Thanks. Bye, everybody. Thank you.
All right, thanks so much.